Hello, everyone, and welcome back to the lecture series on chemical reactions in aqueous solutions. You may recall that a solution is a homogeneous mixture of two or more substances. Solutions can be gaseous, such as air, solid, such as brass, or liquid, such as salt water. Typically, the substance present in the largest amount is called the solvent, while any substance present in a smaller amount is the solute. For example, when a teaspoon of sugar is dissolved in a glass of water, water is the solvent, and sugar is the solute. Our focus here is on the properties of aqueous solutions, those in which water acts as the solvent. Throughout the rest of this module, unless otherwise stated, the term solution will specifically refer to an aqueous solution. Before we move on to studying chemical transformations in aqueous solutions, we should learn about the classification of water-soluble substances as electrolytes and non-electrolytes. You may already be familiar with electrolytes in the context of sports drinks like Gatorade. Electrolytes in body fluids are essential for transmitting electrical impulses, which are critical for physiological processes such as nerve signaling and muscle contractions. Generally, an electrolyte is a substance that dissolves in water to produce a solution that conducts electricity. In contrast, a non-electrolyte is a substance that dissolves in water to produce a solution that does not conduct electricity. Every water-soluble substance falls into one of these two categories. The difference between an aqueous solution that conducts electricity and one that does not lies in the presence or absence of ions. For example, consider solutions of sugar and salt. The processes of sucrose dissolving in water and sodium chloride dissolving in water can be represented by the following chemical equations. When sucrose dissolves, the molecules remain intact, forming aqueous sucrose molecules. In contrast, sodium chloride dissociates into aqueous sodium ions and chloride ions. Dissociation is the process by which an ionic compound breaks apart into its constituent ions upon dissolution. The presence of ions enables the sodium chloride solution to conduct electricity. In other words, sodium chloride is an electrolyte, while sucrose is a non-electrolyte. Like sucrose, many water-soluble covalent compounds are non-electrolytes. However, some covalent compounds are electrolytes because they ionize upon dissolution. Ionization is the process by which a covalent compound forms ions when it dissolves. You might recall from high school that acids are compounds that dissolve in water to produce hydrogen ions. For example, hydrogen chloride ionizes to produce hydrogen ions and chloride ions. Acids are one of two important classes of covalent compounds that act as electrolytes. The other class is molecular bases, which are compounds that dissolve in water to produce hydroxide ions. Ammonia, for instance, reacts with water to produce ammonium and hydroxide ions. In a solution of sodium chloride, all of the dissolved sodium chloride exists in the form of ions. Thus, sodium chloride, which is an ionic compound, is said to dissociate completely. An electrolyte that dissociates completely is known as a strong electrolyte. All water-soluble ionic compounds dissociate completely upon dissolving, making them strong electrolytes. In contrast, only a few covalent compounds are strong electrolytes. These include the 7 strong acids, which are listed in this table. A strong acid ionizes completely, producing a solution that contains hydrogen ions and corresponding anions, with essentially no intact acid molecules remaining. Most covalent compounds that are electrolytes are weak electrolytes. A weak electrolyte is a compound that produces ions upon dissolving, but remains predominantly as non-ionized molecules in solution. Most acids, except those listed in the previous table, are weak electrolytes. For example, acetic acid is a weak acid, and its ionization in water can be represented by a chemical equation presented here. The use of a double arrow in this equation indicates a reaction that occurs in both directions, meaning not all reactants are converted to products. Instead, forward and reverse reactions take place, establishing a state of dynamic chemical equilibrium. Although acetic acid molecules ionize, the resulting ions have a strong tendency to recombine and form acetic acid molecules again. Eventually, the ions recombine at the same rate they are produced, resulting in no further change in the number of acetic acid molecules, hydrogen ions, or acetate ions. In weak electrolytes, there is a stronger tendency for ions to recombine than for molecules to ionize. As a result, at any given time, most of the dissolved acetic acid remains non-ionized, with only a small percentage existing as hydrogen ions and acetate ions. The ionization of a weak base is similar in many ways to that of a weak acid, but requires additional explanation. Ammonia is a common weak base, and its ionization in water can be represented by this equation. Unlike weak acids, ammonia does not ionize by breaking into ions. Instead, it ionizes a water molecule. A hydrogen ion from a water molecule attaches to an ammonia molecule, forming an ammonium ion and leaving a hydroxide ion in solution. As with weak acids, the reverse process predominates. So, at any given time, far more ammonia molecules are present than ammonium and hydroxide ions. We can experimentally distinguish between electrolytes and non-electrolytes using an apparatus like this one. A light bulb is connected to a battery via a circuit that includes the beaker's contents. For the bulb to light, electric current must flow between the electrodes. As shown on the left, pure water is a very poor conductor of electricity because it ionizes to an extremely small extent, leaving virtually no ions to conduct current. Therefore, pure water is considered a non-electrolyte. However, when a small amount of salt is added, the bulb begins to glow as the salt dissolves. Sodium chloride dissociates completely in water, producing sodium and chloride ions. Since the salt solution conducts electricity, sodium chloride is classified as an electrolyte. If the solution contains a weak electrolyte, as shown in the middle figure, the bulb will glow dimly due to the lower concentration of ions. In these experiments, cations are attracted to the negative electrode, while anions are drawn to the positive electrode, creating an electric current equivalent to the flow of electrons in a metal wire. The brightness of the bulb depends on the number of ions in solution. While the experimental method I just described can be useful, you will often need to classify a compound as a non-electrolyte, a weak electrolyte, or a strong electrolyte based solely on its formula. A good first step is to determine whether the compound is ionic or covalent. An ionic compound contains a cation, either a metal ion or the ammonium ion, and an anion, which may be atomic or polyatomic. A binary compound composed of a metal and a nonmetal is almost always ionic. This is a good time to learn the names and formulas of some of the most important ions. You will need to recognize these ions in compound formulas. Remember that any ionic compound that dissolves in water is a strong electrolyte. If a compound does not contain a metal cation or the ammonium cation, it is a covalent or molecular compound. In this case, you need to determine whether it is an acid. If a covalent compound is not an acid, consider whether it is a weak base. Many weak bases, such as methylamine, pyridine, and hydroxylamine, are related to ammonia, consisting of a nitrogen atom bonded to hydrogen or carbon atoms. Therefore, weak bases are weak electrolytes. If a covalent compound is neither an acid nor a weak base, it is a non-electrolyte. Now, let's focus on acids, which are generally recognized by the way their formulas are written, with the ionizable hydrogens placed first, as in sulfuric acid, carbonic acid, and phosphoric acid. Carboxylic acids, such as acetic acid, often have their ionizable hydrogens written last to keep the functional group together. Thus, if a compound is an acid, it is an electrolyte. If it is a strong acid, it is a strong electrolyte. In contrast, weak acids are weak electrolytes. To sum up, in this lecture, you have learned that an electrolyte is a compound that dissolves in water to form an electrically conducting solution, while non-electrolytes dissolve to form non-conducting solutions. You learned that both acids and bases are electrolytes. Electrolytes can be ionic or covalent. Ionic electrolytes undergo dissociation in solution, while covalent electrolytes undergo ionization. Strong electrolytes dissociate completely, whereas weak electrolytes ionize only partially. In the next lecture, you will see how certain groups of electrolytes react with one another in precipitation reactions. Thank you for your attention.